This is part 6 of the chemical analysis topic in GCSE AQA chemistry. It is a triple only topic. Due award scientists do not need to cover this. In this final section of the chapter, we're going to look at instrumental analysis. So you need to be aware of advantages and disadvantages of instrumental methods when compared with traditional chemical tests. Traditional chemical tests are the things that you've probably been doing in practicals right the way through. We've just been speaking about tests for positive ions, for negative ions. We're looking at how that can be done with instruments. We're also going to look at how we can interpret results from flame emission spectroscopy when given appropriate data. As always, I'm going to recommend you pause and have a go at the activities for yourselves. In industry, analysis of products, checking on emissions, for example, is a very important part of the manufacturing process. And you can do that through traditional means, but nowadays, with the technology and the opportunities that are out there, modern instrumental analysis techniques are used. So we have the example here of somebody with a titanium hip joint. If you wanted to actually test the quality of it using older methods, you would need an invasive surgery. You would need to go in and analyse that sample. However, there can now be tests done on the patient's blood to see if any traces of the metal from the alloy are in there. So what we're going to start off looking at is advantages and disadvantages of instrumental analysis. And there are some anagrams here to help you through it. So when you're ready, move on, take a look at the answers. So, instrumental analysis, what is the first advantage? Well, first of all, they are very accurate. In many things, think back to the rates of reaction topic where you are seeing how long it takes until you can no longer see the cross in the disappearing cross experiment. That's based on your own perception of when you can't see the cross anymore. Instrumental analysis takes that away. It's much more accurate. It's also much more sensitive. And if it's more sensitive, that means that we can have a greater level of trust in the results. There will be a greater validity. The other advantage is that they are quicker than traditional methods. I will point out this is often a straightforward list some advantages. So learning what these are is important. And finally, it allows small samples to be analysed. Now, I've highlighted the word small there because that's important. If you're testing a sample of something you've made, you want to use as little of it as possible because you're maximising profit. So if we only need a very small sample, that's definitely an advantage. Let's have a think about the disadvantages now. So the process is generally expensive. You are going to need high-grade equipment. You're also going to need special training for the people running that apparatus. So all in all, it becomes a much more expensive process. You can also only interpret by comparing to data from known substances. So unless somebody has gone through the whole process of old school analysis to actually find the information that can then go into a library of resources, it doesn't really work. It works on the basis of comparison to what we already know. So we're going to finish by looking at flame emission spectroscopy. Now, we looked at flame tests earlier within this chapter. We could see there were specific flame colours for specific colours. This takes it a step further forward, and you need to be familiar with some of the principles that we're talking about here. So we heat a sample, and what that does is actually excite electrons. Now, we have always spoken about electrons being in energy levels around the nucleus, and they live in their energy level. We are now saying that if you provide them with energy, they can make the leap to a higher energy level. Now, that requires energy, so energy is absorbed. Those electrons won't stay there, they will move back to their base level. And when they move back down, they release light energy. So what we can then do is look at the wavelength of the light. We had some examples a moment ago, because the wavelength of the light will give a very specific pattern, as we can see here for hydrogen, for mercury, and for neon. We can also look at the intensity of the light. If the light is more intense, that means there is a greater concentration. So if you have got things like mercury that are toxic and that were to get into drinking water, we would be able to look at the level of concentration. We would be able to prove it was there by looking for the characteristic wavelength in the flame emission spectroscope. But we would also be able to see just how concentrated it was. So a little question to finish off. Have a look, see what you think. So what is in figure 2? Well, what we're doing is comparing to a library of known data. And if I take a look up here, I can see a line and I can see that line there. I can see this double, 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 double. This is fitting potassium perfectly. Almost perfectly. There is one extra line here that cannot be accounted for within potassium. But if you go one element up, you can see that that's in line with the one line present on sodium. So that tells us that we have got sodium and potassium present. That takes us to the end of this video and the end of this topic. Thank you for listening and goodbye.